Hello friends and welcome to this update on my current work. So I've been working on pathfinding, but now after the pathfinding is done, we need to take care of what happens between the agents. Right now, the way the pathfinding algorithm works is an agent is going to ask the algorithm, hey, I am positioned at this position here. I need to go to that goal there. Where do I go next? And based on the terrain data and the static obstacles, the pathfinding system will tell the agent, well, you should go in this direction, in a specific direction that's calculated. And then the agent will move there using a velocity vector. Now, the thing is, all of this doesn't include for the fact that there might be other agents in the way. And we really don't want to have the pathfinding algorithm deal with that kind of problem, because that would make the algorithm very, very inefficient. However, what we can do is, well, have the agent make some extra decisions afterwards to avoid possible collisions with other agents. And how can we do this? Well, there are several solutions, but one of the ones I found was reciprocal multiple body collision avoidance. Now, this is a pretty interesting paper, but it does a lot of mathematics and I'm still figuring everything out. But right now, what I'm working on is this A and B, and I'm soon going to have to tackle the C part. So what happens if we have an agent A and an agent B? And agent A would like to know, hey, what are the velocities I could use that would not result in a collision with another agent? And so let's say B is the only agent in the vicinity. So A is going to say, oh, there's B here. I'd like to know more about him. And so that algorithm is going to do several steps to determine what is called a velocity obstacle. So the velocity obstacle is the domain of vectors, of velocity vectors that would result in a collision with B. In a collision with B. So as you can see here, we look at A from the standpoint of we look at the standpoint of A, and A would then be at the origin. And this point here would be where B is relative to A. Now, this circle here has a radius that is the combined radius of A and B. So this means that if we are outside of this circle, if we move and we are any position outside of this circle, those positions will not result in a collision with B. So anything inside the circle will result in a collision with B, should B not be moving. That's an important thing about the algorithm here, is it considers that B is not going to move. And then we reevaluate at a specific time step, we reevaluate. So how does this work then? Well, given a time step, here the time step is 2 seconds. So we are going to reevaluate the velocity obstacle every 2 seconds. Well, we don't want to end up here in that circle. So we can also not end up in any point beyond this, because that means we would have gone through the circle. But all of the vectors that are in the white zone, they are valid velocity vectors that will not result in a collision. So you see this thing here, this is truncated at approximately halfway. Why? Because, well, we say the time step is 2 seconds. So this means that if my velocity, and you know a velocity is expressed in units per second, if I have a velocity of 5 and this is 5 away, well, if I'm checking every second, I can't move by 5. But if my velocity cannot be 5, or maybe like, well, 5 minus, RA plus RB. So I don't want to end up here. But if I check every 2 seconds, well, my velocity cannot be more than 2.5, because if I do more than 2.5, I might be hitting B within the next 2 seconds. So the bigger the time step is, the less this triangle is truncated, and the smaller the time step is, the more the the triangle is truncated. And so let's see this in action inside of Unity. So we have an agent A and an agent B. And so we're on the perspective of agent A, and if we start playing, then we can see the domain here. The velocity obstacle is anything that's inside this red shape. So if I move here with A, you can see that this moves along. If I'm here, bad news. I am in a collision, so there's no way to escape the collision. So the domain is just everything. There is no domain where a velocity wouldn't result in a collision. So this here tells me what kind of velocity vectors I can use. And if I change the time step, say, hey, I want to calculate at a smaller frequency, well, these are that's the updated vectors, right? So now I have smaller vectors. If I really want to go in that direction, I would need to use a much smaller velocity. So the goal then is to find a velocity outside of that range. And that's the next step for me. That's going to be the next step in determining which vectors I can use. And also, if I decrease the time step, well, I could have velocity vectors that go far beyond this, because, well, if I check every fifth of a second, well, I can move up till here in a fifth of a second with a velocity vector that is this big, because then I'm going to check the next time, and then I'm going to use a new velocity vector. So that's the idea. That's how it works. Now, if we want to see the viewpoint of B, of course, because we suppose that B is not moving, but B is also doing his own thing, right? So if I put it back to 1 here, so they both have their domain of valid things, of valid vectors. And so they are going to avoid each other. And the way you determine the algorithm is going to determine how they're going to move. So if I say you have to prefer looking for a new direction to the right, so they're going to both go to their respective right, which means that B is going to move this way and A is going to move this way, and they're going to avoid each other. Right now, of course, I'm not doing it. This is just representing the different values that I've calculated. And now my point is to be able to determine, hey, is a given velocity vector inside the velocity obstacle? Second step. And then third step is determining, hey, from there, how do I now get to choose which new velocity I'm going to give my character? But this is all work in progress, and I can't show any of that yet. But that's it. Hope you liked it, and see you next time.